Welcome back to ECE 501B. Homework 2 is due on Monday evening next week. I have, and what I didn't put up here, there are now 2 lectures that we didn't have in class that are available on D2L. That's lecture 2.2 and lecture 2.3. What I didn't put up here is I have also posted on D2L exam number 1 material for you to practice or to see what kind of questions or problems you might see on exam number 1 in this class. I would point out that in between the material on the basis vectors and dimension, I haven't explicitly provided material on Proposition 213. That's in the second edition, or it's labeled as Equation 234 or Statement 234 in the third edition. And that concerns really if you start with the vector space V and any subspace in it U, then you can actually create a direct sum subspace W that will complete V. That's essentially what Proposition 213 says in Chapter 2. But again, there's additional material now on basis vectors. How do you reduce a spanning list of vectors to a set of basis vectors? How do you expand a set of linearly independent vectors that don't yet span the entire space? So how do you extend vectors to form a set of basis vectors? That's section 2.2. Dimension is now trying to clear up some of the concepts with ideas or with notation, and what do we really mean by dimension. And today what I want to do is start chapter 3, material, which is now concerned with mapping. So far we've really just sort of started to learn a little bit about vector spaces and what we can do relative to those vector spaces as far as being linearly independent. What do they span? Can we get a basis set on a vector space? Now can we start mapping between those vector spaces, whether the vector space is the same on the input and the output or whether it's different. We want to now talk about the maps between vector spaces, and in this class we will usually be focusing on linear maps. We'll start that discussion by saying what properties a linear map has to have, and that's additivity and homogeneity. Then we'll go through many different examples of these maps, some of those being linear maps and some of them not. Then we will actually look at this abstract concept where we actually say, oh, these linear maps themselves could actually be considered a vector space. So that's a little bit more abstract of a concept, and we'll try to talk about that. Then we will start to examine some particular subspaces associated with linear maps, and in particular null space and range space and some of the consequences associated with those different spaces or subspaces in this set of vector spaces V and W. So let's start then by just drawing pictures maybe, but let's start chapter 3, which is dealing with linear maps. Trying to get a visual perspective on that and then see what that means algebraically. But a linear map is a function, and by that we're going to start in one vector space and map into a second vector space where maybe this vector space, the input vector space, we might say is V. The other one, just to be more general, might be W. And we are now interested in this function that takes us from one vector space into another. And a linear map is a function that takes as its input an element or vector of a vector space V, and uniquely identifies an element of the vector space W. And we might write that more symbolically as T, which is this map T, such that it's a map that takes V into W. So this is, let's say, from V to W. The picture then is we have some vector space, underlying vector space that we're considering our input vector space. We have this linear map that then takes us into another vector space that may be the same or it may be different, and it uniquely maps between an input element into an element in the output vector space. So this map is the function. We are going to be worried about a linear map. Right now I've just really said it's a function. Let's now show what properties this function needs to satisfy or possess in order for it to be a linear map. So this linear map requires two properties. So this, let's say, map requires two properties to qualify as a linear map. The first property is additivity, which really says if you now have two vectors from your input space and you add those together and you take that sum of vectors and map them through T, then that should be the same as taking each of these vectors by themselves and mapping through T and forming their sum at the output side. Meaning T of U plus V needs to equal T of U plus T of V for all vectors U and V in the underlying vector space V, or in the input space, input vector space. That's one property. The second property is then this homogeneity property. That one says then if we scale a vector V by some scalar in our field of F, then map it through this map, that should be the same as scaling the result of taking that original vector and mapping it through T and scaling that result with this scalar A. And that should be true for A that are coming from our field, typically in this class either the reals or complex field of numbers, and any element V in our vector space. We need these two properties in order to have this map between V and W to be a linear map. They need to have this additivity property and homogeneity property. together, these properties make a map linear. And the book makes the following comment, and I will go ahead and be consistent with the book as far as we may mix notation. By that I mean I may write T with V explicitly identified as the argument of T, this map, or I may just say TV. And hopefully you all brought your remotes so that you could watch TV. No, not now, but I may use either of these two notations. Also, another notation that we will use is this script L of V comma W. That's actually defined to be the set of all linear maps T that take V into W. So the script L VW, that explicitly identifies the input vector space V, the output vector space W, and the script L says that, oh, that is the collection or the set of all such linear maps from V to W. If we want to refer to all such maps, we would say that's this set L of VW. Luckily, this concept of a linear map is a very broad category. So this linear map is an extremely broad category. Let's now look at some examples from Axler, the textbook. We could have a zero map, which this zero map then simply maps all elements of our input vector space V to the additive identity in W. And it may get a little bit confusing as to what we're writing, but this is a way of describing that with an equation. We could say 0V is equal to 0, but that 0 is overloaded. On the left-hand side, that actually represents a map. On the right-hand side, it's the additive identity in W, which really is saying that the notation that we will be using is in fact overloaded, where we are now using the same symbol, 0, to mean several different things. And hopefully you'll be able to understand what that 0 represents from context. but that's the zero map, for example. What about another map, which might be referred to as the identity map? This linear map now maps each element in the input vector space V back into itself. You started a vector V. After the linear map, you get back vector V. And we might refer to that as I, which is this. It's a linear map in the set of linear maps between V and W. Such that IV, you're not on life support, you don't have an IV, but IV is equal to V. Wow, this allows for a lot of different interpretations. Some of these are even overloaded more than you would have thought from a math class, right? Maybe, maybe not. Let's move on. That's the identity map, but that's just mapping a vector back into itself. Those were pretty benign maps, the zero map and the identity map. We could also have a map T that's, let's say, a linear map from the set of polynomials on the reals into the set of polynomials on the reals, which is, let's say, the differentiation map, where if we now have, let's say, P of X, for example, let's just say P of X happened to be 3x squared plus 2x plus 7, then what we're really saying is this map T, this differentiation map, operating on P is the same as differentiating P, differentiating the polynomial P of X with respect to X. Where in our example, if we said over here TP, that's now 6x plus 2. And is it true that that's a linear map? What are the two properties that have to be satisfied in order for that map to be a linear map? We have to have it possessing additivity, which now says if we have two polynomials, P and Q, and we add them, and then we operate on those with this differentiation map, T, then that's the same as saying P plus Q, or the derivative of P plus Q with respect to X. But we know that the derivative of a sum is the sum of the derivatives, based on what we know from calculus. This now becomes P prime plus Q prime, but that is just TP plus TQ, and that is what we needed for additivity. Similarly, for homogeneity, if we have a polynomial P and we scale it by some scalar A in our field of numbers R or C, then that's supposed to be, or that's equal to, the derivative of AP, but we know a constant can be factored out of the derivative. But we also know what the derivative is in terms of this operator. It's TP. So this now becomes A T of P, and that's what we needed T of AP to equal A of TP for homogeneity, and we do. So the differentiation operator or differentiation map is a linear map, where in this case we were saying we're going from the set of all polynomials with real coefficients into that same set or vector space. What about integration? And here we could look at two different types of integration. We could say, well, we have indefinite integration and we have definite integration. For indefinite integration, we have a map T that maps from this set of polynomials, or this vector space of polynomials on the reals into the same vector space. If we have a definite integral and we're integrating from, or our input space is the set of polynomials on the reals, what is the output vector space for a definite integral? It's now just the reals, isn't it? It's now the real line. That's now our output vector space. And those two maps are linear maps between those different vector spaces. Another example of a linear map, let's say dimension changing. Suppose that our map now is going to be a linear map between R3 and R2. Now we're going from a three-dimensional space to a plane. And an example of that might be, suppose that we now have this linear map T operating on a vector in V. How big or what does that vector in V look like? It has three components, doesn't it? It has three coordinates. Let me just call those, I'll get really creative, X, Y, and Z. This is our three-dimensional space. What we want to do now is end up in a plane. And just for illustration purposes, suppose that the first coordinate in this plane is now given from those three coordinates in R3. It's now 2x minus y plus 3z. Suppose that will give us the first coordinate in our plane, and the second coordinate is then 7x plus 5y minus 6z. That combination of 2 points as a function of x, y, and z forms this plane. And we were starting anywhere in this three-dimensional space. We're now mapping onto the plane defined by those two combination of three variables. Another example, what about the projection map? Meaning now we're going to go from R3 into R3, but we want to project within this three-dimensional space. For example, maybe t of xyz. So we're operating with this linear map on this point xyz in three-dimensional space. Let's now say that we want to just project down orthogonal in the z direction. So if you view this lecture surface that I'm walking on as the xy plane and the vertical direction as the z plane, you could think of xyz being my head. Now with this projection map, all I'm doing is giving you the coordinates of where I'm standing. I've now projected in the vertical direction, and I now am giving you xy where I'm standing on the plane. And that's the projection map. And that could move around that point. I apologize for those of you that are listening. You can't see this vertical change in the z on this example, but those in class, or maybe if you're at home, you can walk around in your living room and vary z by making yourself shorter and taller. Yes? Yes, so now this XYZ, that will give you a unique mapping. And now it may give you another XYZ, might give you the same XY, but that gives you a unique mapping from that XYZ. Meaning, I think the question was, if you're standing in the same spot and you start changing your Z, aren't you keeping the same XY? Yes, but the mapping is still unique. If you followed my head, now I'm going here to XY. Now I'm going from here to XY, and it's a unique map in each case. Even though XY is not necessarily a new point for each XYZ. You can have, what, an infinite number of points above that XY location. You can go positive and negative, but each of those is uniquely mapping to XY. Let's see if this projection map is linear. And we can do that, or let's just do it in a direct proof fashion. By that, let's just sort of pick some variables and work with those. For example, let's let U be U1, U2, and U3, and let's let V be V1, V2, V3, which have been arbitrarily selected from our input vector space, capital V. With those arbitrary choices for U and V, we can take U plus V through this linear map T, where this, well, I'm sorry, this map, we're trying to justify that it's linear, this map T, but now if we start with U plus V, that's now saying we are simply looking at the sum of the coordinates of those three coordinates in U and V. We have U1 plus V1, U2 plus V2, and U3 plus V3. That's all we mean by T of U plus V. This projection map, though, what will happen when we map those three coordinates through this map T? What's the result? We have u1 plus v1 sitting in the first coordinate, u2 plus v2 in the second coordinate, and a 0. Again, we're projecting in that third direction down to the first two coordinates plane. But now we can go in the other direction. We can say, well, that's u1, u2, 0 plus v1, v2, 0. And now let's just keep backing towards what that means in terms of our map that we created or that we're investigating. u1, u2, 0 we could get by looking at or mapping u1, u2, u3 through t. And now that is just tu plus tv, which verifies the additivity property. The homogeneity property says let's start with some number or scalar in our field of numbers, R or C, and use that scalar to scale the vector u. Then that's scaling each coordinate with the same scalar alpha. If we now pass those through that map, we end up with alpha u1, alpha u sub 2, 0. But that scalar can be factored out of that vector. And now if we just look at this resulting vector u1, u2, 0, we could get there by mapping through t of u1, u2, u3. And that now verifies that the homogeneity property is true. We now have the two properties, and T is then a linear map. Let's look at another map. I'll refer to this as the translation map, where let's say this map T is now working in the plane. Now I don't have to worry about where my head is located. I just have to worry about where my feet are on this floor in the front of the classroom. And suppose that this map is such that T, operating on an arbitrary point u1, u2, translates that into u1 plus 1 and u2 plus 2. So I'm now translating each of those coordinates a given amount. Is the translation map linear? Does it satisfy those two properties? Can you come up with a counterexample? And one that you may always want to try in your investigation is the additive identity. Is your vector space non-empty? Essentially, is your output vector space non-empty? Meaning, let's see if we can illustrate that this is not a linear map with a counterexample where the counterexample is going to be based on the additive identity in the output space, output vector space. Is the additive identity mapped onto itself? Where in this case, since we're in R2, this additive identity is actually the zero vector. Meaning here we have, let's say, t of 0, 0. That's the zero vector. And we want to know, after going through this linear map, after going through this map, t, do we end up at 0, 0? And I think it's clear that that's not going to be the case from the way that this map is defined. We plug in 0 and 0 for U1 and U2 on the right, and we end up with 1, 2. I think it's clear that that's not 0, or that's not the zero vector in this R2. And in fact, that actually verifies that this map does not satisfy the homogeneity property when this zero vector does not map into itself. Let's see if we can explain what we mean by the zero vector needs to map into itself through a map if this map is a linear map. Explanation for why a linear map should map the additive identity onto itself. Now, what's the relationship or what is the expression that we have relative to homogeneity for a generic vector and a generic scalar? From homogeneity, we said T of alpha, let's say V, is equal to what if we have the homogeneity property in place? It has to be scaled linear map of V. That's the homogeneity property. What we're utilizing now, we're going back to chapter 1, and we're looking at proposition 1.4. I'm sure you all have that memorized. And class, what is that? That says that 0v, so we scale a vector with the zero scalar, and what does that give us? 0. So this is what we're going to use in many different places. If we have a vector from our input vector space, which we'll call V, and we scale that with the zero scalar, then what do we end up with? We end up with the zero vector in the result. That's proposition 1.4. Now let's apply that in general to this, or to the homogeneity property, to justify why we can say that the linear map needs to map the additive identity back into itself. Why does T of 0 equal 0 for a linear map, essentially? First, let's let A, the scalar, be 0, and that exists or is true in either R or C, the reals or the complex numbers. And let's let V be any element in our input vector space V. Now, I'll try to fit this all on one line. Now I want to look at T of 0 times V. What does that equal if I now said, oh, this is now, let me apply proposition 1.4 on the argument of this map. So T of 0 times V must equal T of 0. Now, by homogeneity, if this is a linear map, then let me say here I want to apply homogeneity from there to here. What would I write down now on this rightmost equality if I said T of 0 times V by the homogeneity property is supposed to be the scalar times the linear map on the vector V? Meaning this needs to be then 0 T of V. But T of V is a vector in the output vector space, scaled by 0. So again, applying proposition 1.4 to this equality, where now you're viewing this as some vector, W, you now have W scaled by 0. What's going to be the result? That's now this 0 vector in the output space. And what can we conclude from this? Now, if you sort of look at what's happening here and here, all of these things are supposed to be equal. Let's extract two of those pieces that are equal, the two that we want, and say, oh, the 0 vector mapped through T must equal the 0 vector. And that's what I'm trying to indicate in green, dashed. This is now saying that we are now showing that the additive identity needs to map to itself if we have a linear map. The linear map satisfies the homogeneity property, which is why we were able to sort of make this equality between expression 1 and 3 in that chain of equalities. We used proposition 1.4 a couple of different times in that chain, and then we compared or just extracted expression 2 and expression 4 in that chain of equalities to end up with the result that we wanted, which now says that if you're trying to show that maybe there's a map and you want to verify or illustrate that it's not a linear map, if it doesn't map the additive identity back into itself, then that violates this condition, and so you know you do not have a linear map. And we used that fact as our counterexample here for this translation map. That was our counterexample, as we were saying, is the additive identity mapped back into itself? It's not, so this must not be a linear map. Is that a question in the back? I have to put my binoculars on. So P of X is an element of this set of all polynomials. Now, what's your question? So now we're going to map that, or use the differentiation map. So now we're saying T is the differentiation map. So that on this example, if we said TP, that's now 2x plus 2. Correct. So this, no, so the question was, it doesn't look like this differentiation map is mapping the additive identity into itself. But what's the additive identity in the set of polynomials, or in the vector space of polynomials? It's the zero polynomial. So you now have 0x cubed plus 0x squared plus 0x plus 0. You differentiate that, and what do you get? You get the 0 vector. So you're starting with P of x equal to x squared plus 2x. What I'm trying to say is that's not the 0 vector in this set of polynomials. Is that okay? So we're using the differentiation map appropriately here. We are getting a non-zero result after passing through this linear map, which is a differentiation map. But this is not yet looking at the 0 vector in that original vector space. In the P, the script P of R, the additive identity would be the 0 polynomial. And that one, if we differentiate the 0 polynomial, I could maybe have even done that as a freshman. That would have given me 0, but then I probably would have messed up because it was too easy, right? You get this polynomial, and they go, what's the derivative of 0? Uh-oh, this is a trick. What's the trick? Did that answer your question? So that's what you need to identify first, obviously, then, and when you're doing this, is what's my additive identity, and can I show that this, and if you show that that is contained, or that the linear map does map, or the map that you're investigating does map the additive identity back into itself, that's not necessarily justification that it's a linear map. But if it doesn't, then that's a counterexample for eliminating that as a linear map. Now, let's get into using something that we aren't yet going to define. well, we'll define it, but we won't talk about it too much. But can I be any more unclear? Let's look at norms and this linearity property. Norms in and of themselves, we will discuss later. I'm just going to define those as something, and we'll view those as maps and see if they do, or any of these, or one of them, is it linear. The norms we are going to discuss later, but I think it's kind of nice to be thinking about this concept anyway. And to do that, let's just define this generic vector x that we will say is of coordinates x1, x2, up to x sub n, such that each of those coordinates is an element of our field of numbers f, where f is either the reals or complex. So now we just have an n vector for x. It's finite in length. Here, let's make some definitions. The one norm. So the norm I'm going to represent by two vertical bars, and I'm going to specify the type of norm by the subscript on the lower right. This is the one norm of x. What is that? That's the sum. So the answer was okay. I'm going to try to make it a little bit more precise. So we're looking at each of these coordinates in our vector x. We actually want to take the magnitude of those because x we can allow to be complex. So that now we take the magnitude of the first coordinate, we raise it to the first power. We take the magnitude of the second coordinate and raise it to the first power. I'm just doing this because that's the generalizable strategy that we're going to be using. And then we continue that. And now we raise this to the 1/1 power. Which is we're not doing anything to it. But in general, this would be that, where the blue one is coming from the one norm. And the 1 powers on these coordinates, magnitudes, is coming from the one norm. Or you could say that this is now the sum of the magnitudes of each of these coordinates raised to the first power, and we can now sum over all coordinates. That's the one norm. And we could say that this is now raised to the, or the first root of that. What's the two norm? If we can now generalize that idea, I hope that you can see maybe how we could construct or build the two norm. And in fact, this one is the one that we're probably more used to. This is the distance norm, or the Euclidean norm, that you're probably more used to, especially in two-dimensional space. This is the Pythagorean theorem, kind of. But now we have the norm x, its two norm, is going to be the magnitude of the first coordinate squared plus the magnitude of the second coordinate squared on up to the nth coordinate squared, all raised to the 1/2 power. Or this is now the square root of the sum of the coordinates magnitudes squared. That's the 2 norm. And in R2, that's just x1 squared plus x2 squared square rooted, or the distance from the origin in the x1, x2 plane. That's the Euclidean distance, or the Euclidean norm. The other one is the 1 norm. What's that one more like? This is now like if you were doing a street, this would be like the lengths of the street that you're navigating. It's now the horizontal length plus the vertical length if you were doing XY. And it's not the Euclidean distance. This is now like the blocks distance, the 1 norm, which might be important if you were a cab driver. You might want to be worried about the 1 norm versus the 2 norm. Instead of how the crow flies, you might want to know what's the distance using a 1 norm from point A to point B, for example. Maybe you're wondering, what in the world, why are we doing all these norms? Who cares? Did that even come through? All right, so do you see that you could create the 3 norm, the 4 norm? You guys have a few hours. Let's do that. Let's just keep going. What happens if we go all the way? Okay, you're getting impatient. Let's do the infinity norm. What does that look like? We want to know what's the norm, the infinity norm of this vector x. And the x is in coordinates, Nevada coordinates long or big. If you take this idea of the 1 norm, 2 norm, 3 norm, 4 norm, what's going to start falling out if you think about what happens in the limit? Now you're taking each of these coordinates or components of your vector and you're raising it to a really, 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 really big power. What happens to the relationship among those coordinates? It's going to pick off or start to favor the coordinates that has the biggest magnitude, isn't it? Because that one's going to blow up. That's what you're going to be focusing on, is the largest coordinate. And that's the infinity norm. You look at the max over all of your coordinates of the absolute value or the magnitude of those coordinates. Because what are you doing? You're now taking the infinite root after you've raised it to the, well, you're not getting there, but in the limit. And that's now going to pick off just this largest component in your vector. So those are some norms, and I hope that you can now envision all of these varieties of norms, the 3 norm, the 5 norm, but these are the 3 ones that are usually used: the 1 norm, the 2 norm, and the infinity norm. Let's look at the 2 norm. Is the 2 norm linear? Is that linear? So now this is, got caught. So you could flip a coin, right? At least on this. This only has one of 2 answers, yes or no. So this one's pretty good odds. We're not in Vegas, are we? This has better odds than Vegas, 50%. We're kind of close to Vegas, though, aren't we? For those of you listening, you probably don't know what I'm talking about. But is it a linear map, the 2 norm? What am I hearing? I'm not hearing very clearly, but I think I heard no. Let's look at an example. What if we take T, this map that we're defining to be the 2 norm, and suppose that we want to, so in order not to get this confused that, oh, the 2 norm applies to the two-dimensional surface, let's look at the 2 norm in three-dimensional space. Now you can think of as having coordinates of a box, and you're trying to get from one lower coordinate or the origin in that box up to another coordinate. That's essentially what you're doing, and you're mapping that into a distance that will just be a real number. This T then is a mapping from R3 to R. And we want to then sort of verify or illustrate why this is or is not a linear map, why T, being this map associated with the 2 norm, is not a linear map. And a very good way to do that is to just come up with a counterexample. For example, we can show that, let's say that we have an x vector that's 1, minus 1, 1. So we go 1 in the positive x, minus 1 in the y direction, and up 1 in the z direction. And let's let y go 1, 1, minus 1. With that choice of two arbitrary vectors, actually these are two specific vectors in R3, that's all we need for a counterexample. I hope it's clear that the 2 norm of x and y added together is not the same as the 2 norm of x plus the 2 norm of y. That's what we would need to equality in that expression in order for this map of the 2 norm to be linear. That would be one of the properties. And which property is this? I'll give you a hint. So additivity is actually violated. And if you want to verify this, maybe you can check my math. I came up with the 2 norm of x plus y being 2, since if you add those up, you end up with 2, 0, 0 for x plus y, and now you're looking at the 2 norm of 2, 0, 0, and that's not equal to the square roots of 3 added up, or 2 times the square root of 3, and the last time I remembered, square root of 3 was about 1.7. So this is now, and I don't think 2 is close to 3.4. So there is a map a norm mapping that is not linear. All right, now let's give you an alert that we're now talking about something that's kind of an abstract concept. And what we're talking about now is the following. We want to make or discuss or talk about the fact that you can create a vector space out of linear maps. An interesting development is that we can turn the set of linear maps, which we've said we will label as script L of v comma w, into a vector space. Again, this fact is an example of an abstract vector space. This is not like three-dimensional space and two-dimensional space. This is now a more abstract concept. Now we're talking about these linear maps being a vector space. Now, don't get confused because I'm going to put things in quotes. These aren't air quotes. Maybe I'll make some air quotes, but this will be quotes in writing. We have a set of vectors, and that vectors is in quotes, and those vectors are the elements that are in this set of linear maps. Those are the vectors. We also need a set of scalars and those are going to be from either R or C in this case, let's say just F. And now what we need is we need our two binary functions. We need an addition or a vector addition and a scalar multiplication with these vectors and scalars. So here is our vector addition, and this is our scalar multiplication. 1. Suppose that somebody gives you two maps, S and T, that are both linear, and they map between vector space V and vector space W. Now, with those two maps, we can define their vector addition, S plus T, and that likewise is mapping between V and W, where S plus T operating on some vector is S operating on that vector plus T operating on that vector, and that's true for all v in our input vector space. We also can select an arbitrary scalar in our field of numbers and some arbitrary map from our set of linear maps between v and w. And now alpha t, just scaling the linear map isn't going to remove it from our set of linear maps. So alpha t is an element of VW, where alpha t on V is now equal to alpha TV. Which really is a quick way to sort of say that it satisfies all the properties of a vector space. So this collection of linear maps from a vector space V to a vector space W, that in and of itself is a vector space. Now, if I ask you a question relative to that concept, what is the additive identity of the vector space? It just maps everything to zero. It's really just the zero map, isn't it? Because we want that additive identity when added to another linear map to give us the linear map back that we started with. So now the zero map will perform that function. That's our answer. Now, it's actually possible for some of these maps, let's say for some pairs, of linear maps, we can even define multiplication of linear maps. And I think what this should start triggering is a lot of times these linear maps, especially when they're from certain, let's say, r-dimensional or n-dimensional vector spaces, these linear maps can be equivalent to matrices. So now we're just saying that suppose that we're given some linear map T from U to V and some other linear map that maps from V to W. Then in fact, in some cases, we could first map through T and then S, and that would be a linear map from U to W, where we're actually taking this ST operating on V is really equivalent to S operating on TV. But what we have to realize is this sort of multiplication of maps, of linear maps, that only works when we have some compatibility conditions. Only works when the output space of the first map, let's say T, is the input space of S. Now, what else can you say, just to wrap up, about this multiplication of linear maps? Does it matter the order with which we try to do that mapping? If I can go T and then S, can I go S then T? Not necessarily. So these linear maps may not be commutative. So this multiplication, or this multiplication of linear maps, is not necessarily commutative. Meaning we're not guaranteed that ST is going to be the same as TS. And we'll pick up at that point talking about some of these important spaces relative to linear maps next time.